Okay, welcome. So last time in Physics 157, we talked about adding heat to various materials and how to quantitatively understand the temperature change that that produces. Or the other way around, understanding how much heat we have to add to a material in order to produce a certain desired temperature change. So our basic formula was this one here, where the amount of heat that we need to add is proportional to the change in temperature that we want to achieve. And we can understand that because temperature was related to the average kinetic energy of the molecules. And so if you want to increase the temperature, we need to supply more energy. And we see that it's just proportional. If you have more matter, then you're going to need to supply more energy. So for example, if you have 2 bricks and you want to heat them up by the same amount, the same temperature change, then you're going to need to supply twice as much energy as compared to just heating up 1 brick. And so that's why we have the M here in the formula on the right-hand side. So the amount of energy is proportional to the mass. It's proportional to the change in temperature that you require. And then finally, there's this proportionality constant, the specific heat or the heat capacity. And that's just a basic property of the material that you're talking about. And so you could look it up in a table. What is the heat capacity for copper or water or ice? Its units are joules per kilogram per Kelvin. And the way to understand the number C is it's the energy required to raise the temperature of 1 kilogram of your material by 1 Kelvin. Sometimes you'll see a molar version of this formula. The only difference is that instead of specifying the mass of the material, you specify the number of moles of the material. And then the constant capital C is the molar heat capacity. It's the energy required to heat 1 mole of the material up by 1 degree Kelvin. And so we have various different values for either specific heat or molar heat capacity, depending on what material you're talking about. And it's interesting to see that these numbers vary quite a lot. So if you compare lead to water, then it takes way more energy, more than 30 times more energy to heat up an equivalent mass of water compared to that mass of lead. And I wanted to talk a little bit, just briefly, about why it would be that different types of molecules have different heat capacities. So why is it so much harder to heat up water compared with lead? So in order to understand this, I want to do a demo, just a virtual demo. And so in the demo, I'm going to show you what it looks like kind of at a molecular level. It's a simulation heating up a very simple molecule, argon. So just a gas of these simple single atom molecules. And then I want to compare that with what it looks like heating up water molecules that are a little bit more complicated. And so you can try to think, what is it that would cause maybe the heat capacity per molecule or per mole of water to be larger than the one for argon? So let's stop the sharing. I'm going to share a YouTube video. That should play automatically for everyone. Okay, we're back here. Share my screen again. Okay, so what was the thing we noticed? So what you probably noticed was that in the case of the water molecules, when I added energy, when I heated up the water molecules, they started to move faster, like the argon molecules, but they also started to rotate a lot more than they were rotating before. And so we can understand that some of the energy that we added to the system with water went into making the molecules move faster, went into increasing their kinetic energy, and therefore their temperature, the temperature of the material. But some of the energy went into increasing the rotational energy of these molecules. And that's not directly determining the temperature. So in the second case, only a part of the energy actually went into increasing the temperature. And so we can understand that for water, it would require more energy input to produce a similar temperature change compared with the argon molecules. And if we have even more complicated molecules, then we might have different kinds of vibrational modes as well. So if we had a really complicated molecule with lots of parts, then we add energy to that system, and different parts of that molecule could be vibrating around. And if you look at let's look at the molar heat capacity, which is a good idea. It gives you a good idea of how much, what the heat capacity just per molecule is, or per mole of material. You see that the largest values are for these fairly complicated molecules: ethylene, glycol, ethanol. These have several carbons and hydrogens in a chain, and those are the ones where if we add energy to the system, then there's a lot of different ways that energy could be distributed into all sorts of different vibrational modes, into rotations, and then only a smaller part of the energy is actually going into making the entire molecule move. Okay, so this is kind of how to understand why these molar heat capacities are different. To get to the specific heat, we're basically just dividing that by the molar mass. Okay, how much does the molecule actually weigh? So there's an analogy that I kind of like for heat capacity that helps you visualize what's going on. And so the analogy is to imagine that energy is this orange liquid, and different materials are represented by these containers that can hold the orange liquid. A material with a relatively small heat capacity corresponds to a narrow container. It's like there's only one place where the energy can go, and it's kinetic energy. And so as I pour it in, then the height, which is our analogy for temperature, rises relatively fast. For more complicated molecules, where we have the possibility of kinetic energy and vibrational energies and rotational energies, it's like a container that has more parts to it. And now if I pour in the orange liquid, it gets distributed between the different parts. And so the temperature, which is like the height of the water, it goes up more slowly. So the main thing I want to do today is a detailed example of a problem that's similar to something that you might see later on the midterm, or in tutorial you'll see something similar. So this is one of your standard kinds of problems that we'll see that uses the heat capacity formula and the formula relating heat and temperature. And it goes back to the example from last class, where we had a brick or an object at 100 degrees at a mass of 1 kilogram, and it was put in contact with another object also with a mass of 1 kilogram. And we understood last time that even if one is 100 to start with and the other is 0 degrees Celsius to start with, you don't necessarily end up at 50 degrees Celsius. You might end up at some other temperature, and it all depends on what is the heat capacity of the different materials. So when we have some heat transferred from one to the other, that change in the energy of one material might result in a bigger change in temperature than for the other material. So here we're saying that the 100-degree object has a heat capacity of 300 joules per kilogram per Kelvin, and the other material has a heat capacity or specific heat of 900 joules per kilogram per Kelvin. And we want to calculate the final equilibrium temperature. So you can work through this, pause the video when you need to, and I'll tell you as we go what my solution would be. And the strategy is going to be very similar to other problems that we've solved. We're going to think about, after kind of visualizing the system and drawing the before and after picture, defining our unknown variables, we're going to think about the individual parts of the system, understand what's happening to those individual parts, and then we'll understand how the parts are related, and then we'll have all the information we need to solve the problem. So take a moment to draw some before and after pictures and think of what our unknown variables are. So here's what I came up with. So in the before picture, I'm showing that we have one object at 100 Celsius, we have another object at 0 Celsius, and this first object, we have a specific heat that's smaller. The second object, the specific heat is larger. I've written down the mass. In the final picture, what we know is that the two objects are in equilibrium. So we know that they have the same temperature. We don't know what the temperature is. That's what we want to find. And so I've introduced this variable t as our unknown for the problem. So next, we're going to look at each of the parts. We'll look at what happens. Oops. My mouse is... Let's turn that on again. My mouse is failing to cooperate. I can do it with the keyboard. Okay, so we're going to look at each of the parts, and we're going to see what is the temperature change in that part and how much heat is flowed into that part. And then we'll relate these things for the two different parts. So I want you to think about this question. This is starting with the object that was initially at 100 degrees Celsius. How much heat was added during this process? Okay, and so you think about that for a minute. I will try to recover my mouse. Oh, there it is. All right, well, you've had enough time, hopefully, to think about it, answer the question. So we're basically going to use the formula up at the top. Q equals mc delta T. And there's just a couple of things to understand. So one of them is that when we talk about delta T, it always means the temperature after minus the temperature before. And so for this problem, the temperature after was T, the temperature before was 100. And so our formula for heat for the first object is going to be Q equals M, which is 1 kilogram, C, which is 300 joules per kilogram per Kelvin, times delta T, which is T minus 100. Okay. So the answer for that question is C, Q1 equals 300 joules per Kelvin times T minus 100. Now we can do the same thing for the second part. Q2 is going to be the same mass, now 900 joules per kilogram per Kelvin, and then delta T is T minus 0. So I've written those there. One thing to notice is that we expect the final temperature to be between 0 and 100. So the first Q is going to be a negative number, and the second Q is going to be a positive number. That makes sense because Q is always going to represent the heat that flows into a material. And so if we look at the first object, since heat is flowing out, that's equivalent to a negative heat flowing in. The net heat flowing into the 100 degrees Celsius object is negative. And so that makes sense. And Q2 is positive because the heat is actually flowing into it. So we've understood what's happening to each part. So we've written down these quantitative equations relating the heat flow to the temperature of the final system. And now we want to understand how are the different things related? How are Q1 and Q2 related? And so hopefully it should be clear that since we're talking about a totally isolated system, that whatever heat comes out of the first object must go into the second object. by energy conservation, we can't gain or lose energy from our entire system. And so Q1 and Q2 are related in the simple way that their sum has to be 0. So the total energy going into the system is 0. Or equivalently, Q1 has to be equal to the negative of Q2. Whatever heat goes out of the first one has to go into the second one. Now we're ready to find the answer to the question. We just simply plug in our expression for Q1 and our expression for Q2 into this constraint that Q1 plus Q2 is equal to 0. Combining these equations, we see that the terms proportional to T add up to 1200 joules per Kelvin times T, and the remaining term is just this 300 times minus 100, so minus 30,000 joules. There's a 0 here, so we don't get any extra contribution. So there's our equation, one unknown, T. We solve for that, and it ends up giving us T equals 25 degrees Celsius. So we might have actually guessed that that would have been the final answer based on the ratio of these specific heats. So C2 is 3 times C1. That means that it's 3 times as hard to change the temperature of this object compared with this object. Or for a given amount of energy, the temperature change is going to be 1/3 for this one as compared to this one. And so the energy Q that flows out of this one is the same as the energy Q that flows into this one. And so we would expect that the net temperature change from this initial situation to the final situation is going to be 3 times as much for this object as it is for this object. And we see that that would correspond to a final temperature of 25, because then that's a temperature change of 75 degrees for the hot object and of 25 degrees for the cooler object with a higher specific heat. So you'll see various similar problems like that. And the strategy is always going to be to write down some equation that tells you what the heat change is for each object, and then understand how these things are related. In a more complicated problem, you might have extra parts of your system or heat going in from the outside, but it's always going to be very similar. You'll have an equation like this for each part, and then you'll use energy conservation. Going back to my analogy, we can understand this situation with the 2 bricks, where one has a higher heat capacity, as being something like this. Now it's reversed left to right. So the hotter object had a smaller heat capacity. When you bring it together with the cooler object with a larger heat capacity, then the water level equalizes. So energy, which is the orange liquid, flows from one to the other, and the final temperature, which is like the height of the water, it's going to be closer to the 0 temperature level than the 100 temperature level, because the large amount of water flowing in out of this one will cause there'll be a larger change in height compared with this container. Okay, so I want to discuss now the next topic, which is also related to adding heat to a material, but it's a little bit more interesting in what can happen. So if you have water molecules in a liquid, you add heat, the water warms up. We've understood now how to quantify that, how to predict the change in temperature for a certain amount of water. But you know that if you add enough energy to water, then eventually it goes through this dramatic change into a different state of matter. So we want to understand these phase changes and to be able to quantify the amount of energy that it costs to produce one of these phase changes. So the idea of, I'm going to talk a little bit about the idea of a phase diagram. So understanding which phase of matter you have at different temperatures and pressures. So the idea here is you could take some amount of water molecules or whatever other substance you have, place it at a certain temperature, and it'll also control the pressure by, say, using a weighted piston where you can control the amount of weight. And then depending on the pressure and the temperature, you might find sometimes you're in the solid phase, sometimes you're in the liquid phase, sometimes you're in the gas phase, and sometimes you're at these special points where multiple phases can exist at the same time. So this is the phase diagram for water. And you see that at the usual pressure we're used to working at, so atmospheric pressure, then the diagram is what we would expect. For low temperatures, you have ice. Between 0 and 100, you have water. And above 100, you have steam. If we start changing the pressure as well, then we have some interesting features of the diagram. So we already talked about how if you lower the pressure, the boiling point of water decreases, and at some point it actually coincides with the freezing point of water. And so there's this special pressure, 0.006 times atmospheric pressure, and a special temperature of 0.01 Kelvin Celsius, where water, ice, and steam can all exist in equilibrium. If I raise the pressure, there's another interesting point called the critical point. And at that point, the idea is that at any higher pressure than that, you can't distinguish water and steam. So if you increase the pressure of steam, then it's going to become denser and denser and denser. And so the gas phase is going to be more and more like the liquid phase. And interestingly, above that point, 218 times atmospheric pressure, then there isn't even a sharp transition going from liquid to steam. The steam would be so dense at that point, you couldn't tell that there was anything happening. It's really just one phase that is steam or water, whatever you want to call it. So we're going to focus for now on this pressure. Oh, let me mention one more thing about this diagram. Down at low pressures, you'll notice that ice, if you heat it up, it actually goes directly to water vapor. There's no liquid phase. And so that's the process of sublimation. So that happens with other materials like dry ice at room temperature. Instead of melting, it just sublimates. And so you go directly from solid to gas. Okay, so now we're going to focus on regular atmospheric pressure. And so we'll think about changing the temperature along this line. And what we've understood so far is that if you add heat, then the temperature increases, and we've understood the relationship between that temperature change and the change in the amount of heat that you need to add. Once I get my ice up to 0 degrees Celsius, it turns out that I have to add even more heat in order to turn it into water, even if I want to turn it into water at 0 degrees Celsius. So it doesn't automatically melt. I actually have to add energy in order to cause this melting to go from 0 degrees Celsius ice to 0 degrees Celsius water. Similarly, I need to add energy to go from 100 degrees Celsius water to 100 degrees Celsius steam. That's why your water on the stove doesn't boil instantly into steam. Once it gets to 100, you need to keep adding energy and leave it on the stove for a while, and then finally it will boil away. So this slide basically just says what I just said, and it gives a name to this amount of energy that we need to add in order to melt the ice or to boil the water. We call it latent heat. And so the latent heat of fusion is the amount of energy that it takes to melt 1 kilogram of ice. The latent heat of vaporization is the amount of energy it takes to melt 1 kilogram, to boil 1 kilogram of water. So in general, if I have a certain mass of ice or water, and I want to understand how much energy does it take to melt that, then I just multiply the latent heat by the mass. If I have water and I want to turn it back into ice, then I need to take energy away from that. And so in this case, we would have Q equals minus ml. So your sign here could be plus or minus depending on whether it's melting or whether it's freezing. And you just use your intuition. What do you have to do to ice in order to turn it to water? You need to add energy. So Q is going to be plus ml. If you want to turn water to ice, you have to take away energy. And so Q is going to be equal to minus ml. So let's think of a question here related to this latent heat. The graph that I showed, it's some kind of an experiment where we start with ice water. We put that on a burner and we're supplying power to the, we're supplying power, so we're adding energy at a certain rate. 240 watts means 240 joules per second. So we're adding 240 joules per second to this ice water, and we want to understand what is going on with this graph. Why does it look like this sort of hockey stick? And further, can we actually learn something from this graph? Based on the graph, can we understand how much ice was present initially? Okay. So let's talk about just a qualitative interpretation of the graph. So we start with ice water. We're adding energy. And what I said was it takes energy to turn the ice to water. It's whatever ice is there, it requires us to wait some time until we've added enough energy for all of that to become water before the water will actually heat up. Okay. So we can see that this phase here is where you still have ice. And then at some point, the ice is all gone. And now the energy that you add to your system goes into heating up the water. We'll talk in a minute about why it's slightly curved. But for the meantime, we're going to just approximate this as a flat part and a sloped part. And this is the ice melting. And then this is the point where there's no ice left. And now this is the water heating. Okay. So let's try to estimate from the graph how much ice was present initially. So this is probably a good time to stop the video and think about the question and see if you can come up with one of the answers. And I'll do this in detail. Okay. So I'll reproduce the graph. Well, I guess you could see it on the other slide. So here's my time. This is my temperature. We don't really care about the temperature because it's mostly staying at 0 during this phase where the ice is melting. And so what we want to do is relate the graph to this latent heat formula. So we want to understand how much ice was there originally. We know the latent heat of fusion. And so what we're going to need is to figure out how much energy did we add in order to melt that ice. What we're told is that we add energy at a power of 240 watts. So that's equal to 240 joules per second. And so in order to understand how much total power we've added during this period where the ice is melting, we just have to look at our graph. And it looks like we're adding energy for about 700 seconds before the water just starts heating up, before all the ice is gone, and now we're just heating up the water. And so we add energy at 240 joules per second for a time of about 700 seconds. And so that corresponds to an energy, which just using the units is the power times the time. Okay, so power is energy per time energy that we add is going to be power times time. And so that's going to be equal to 240 joules per second times 700 seconds, which is equal to 168,000. So 168,000 joules. Now we're ready to go with our formula relating heat to the mass and to the latent heat. So we can go back here. Now we know the right-hand side, and so we could calculate the mass, and that's equal to Q divided by LF. And now we plug in our numbers. So 168,000 joules divided by 334,000 joules per kilogram. And that's approximately equal to 0.5 kilograms. So the answer for that one was B. And finally, we could return the question of why is this graph curved? So if we had a perfect situation where we were very slowly adding energy to the water so that everything was always in equilibrium, so the ice and the water were always the same temperature, we just add a tiny little bit of energy, what would happen is a little bit of ice would melt, we'll add a little more energy, a little more ice would melt, and the ice in the water would always be almost exactly at zero until all the ice was melted, and then it would go up and the temperature would increase. In this case, we have power at 240 watts. So we're not necessarily adding it very slowly. We have some kind of a burner and we're adding it in a slightly uncontrolled way. And what can happen then is that the different parts of the system may not always all be in equilibrium. So that's indicated in this picture here. So imagine you put this ice water on a stove and you're adding energy. And so if there's a lot of ice there, then it could be more or less that everything is all in equilibrium. The ice is keeping the water cold. But if you are down to maybe one ice cube, then the water far away from that ice cube might start heating up from the burner. And then it'll take a little while for that energy to get transferred to the ice cube. And so this curviness is something that could just indicate that maybe I'm taking the temperature partway between the ice cube and the bottom of the burner. And so because the heat or the temperature is not uniform, then we're just seeing that increase a little bit as the ice melts. If you were to take the temperature right next to the ice cube, it would pretty much stay at zero and then it would start increasing. Or if you kept mixing very carefully, then you could find that, again, if you're mixing and you're adding energy slowly, then you would find a more perfect shape. And that would be something like this. So it would look like, say, increasing. So this maybe would be part of this diagram that we're going to see next time, where this is ice melting and then the water heating up. Okay, so that's all for today's class. We'll return to this next time and we'll do more examples of problems featuring both heating and changes in phase. So we'll see you on Wednesday.